All right, Mrs. Cat back for part 2 of Lewis structures. So I'm going to talk about hypervalent and polyatomic um, ions, so hypervalent molecules and polyatomic ions. We don't deal a lot with with hypervalent molecules because they're not really things that we're going to be focusing on, but you should still know how to draw Lewis structures for these things as they may come up in some example problems. There are some elements that have the capability to provide more than 8 valence electrons. We call these hypervalent. And these, again, are going to have more than 8 valence electrons in their valence shells. And we will see this in non-metals in period 3 or below on the periodic table. We're just going to look at one example of this, and this is going to be phosphorus pentachloride, or PCl5. We're going to start out the exact same way. So we want to figure out the total number of valence electrons that we have in this entire compound to use. Phosphorus is in group 15, so it has 5 valence electrons to contribute. We have 5 valence electrons, or 5 chlorines, at 7 valence electrons apiece. I'm waiting for my iPad to sync up. It's going a little slow. Okay, 5 at 7 apiece. There we go. For a total of 40 valence electrons. Okay, bear with me. I'm going to close this out and pop back in because it is really, really super duper slow. Okay, let's try this again. So 5, there we go. 5 from phosphorus, 7 chlorine, or 7 from chlorine. There are 5 of those. 5 times 7 is 35, plus 5 is 40 valence electrons to use. Okay, there's only one phosphorus. That's going to make it our central atom. It's also less electronegative. The 5 chlorines are all going to be attached to the phosphorus. So I'm going to go ahead and place bonds in between those, and then just kind of get these 5 chlorines around. Okay, this is what we mean by hypervalent. Phosphorus is in the 3rd period on the periodic table. Let's take a look. Okay, there is phosphorus. Okay, period 1, 2, 3 down. Okay, so it can be hypervalent. So 5 bonds, 2 electrons apiece. That is 10 electrons that I've used. I need to use the rest of the 30. These are going to be starting out as lone pairs on our outside atoms. So 10 already. Let's start counting up. 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. Okay, I've used all of my electrons. I have 5 chlorines that are all identical. Okay, let's take a look at one of them. 1 bond, 3 lone pairs, that's a total of 8 valence electrons. That will satisfy chlorine's need, or it doesn't need anything, it's an atom. Okay, but chlorine will now have 8 valence electrons in its shell, giving it a full valence shell. Phosphorus is going to keep those 10. Yes, that's 2 extra, but phosphorus does have that capability to do that. Okay, again, this is an example of a hypervalent molecule. What we will see more of is polyatomic ions. Okay, polyatomic ions are covalently bonded atoms that have also gained or lost electrons to become charged. Okay, the overall charge means that the polyatomic ion is able to participate in ionic bonding. So we have bonds that hold the polyatomic ion together. Those are covalent. Okay, we have ionic bonding that will then happen between that ion and other ions. So there's a little bit of a difference that we have to do with how we draw those Lewis structures for polyatomic ions. I'm going to pull some examples from part 1 for those polyatomic ions because I'm not going to do all of these. So let's look at part 1. Let's do NH4 plus 1 to start out with, and then I'm also going to do an anion example. So I'm going to go back up here. Well, like I said, we're just going to pull from that so we don't have to do more than we need to. So NH4 plus 1 is the ammonium ion. And we're going to make sure that we basically just use the same process to start out with. Count up the total number of valence electrons. The catch is we have to account for the charge of the ion. So nitrogen has 5 valence electrons, 4 hydrogens at 1 valence electron apiece. Now we got to think about that positive charge. Okay, a positive charge means an electron has been lost. So I'm going to subtract 1 from that total number of valence electrons. Okay, 5 plus 4 is 9, minus 1 is 8 valence electrons, which is great. We should not wind up with an odd number of electrons. You should always wind up with an even number because we have bonds that are pairs of electrons and lone pairs, which are pairs of electrons. Okay, so nitrogen, actually I'm going to move this over here. Nitrogen with 4 hydrogens around, that's actually going to use up all 8 of my electrons. Now, the catch with this is that we need to show that 1 electron has been lost. So I'm going to take this out here, move this over a little bit. So I can have space, because what I want to do is I want to put my whole Lewis structure in brackets and then put the charge of the ion on the outside of that bracket like we would the symbol for the ion. That's going to signify that 1 electron has been lost. Okay. Now, to show what's happening with that lost electron, we can think about what is actually going on with our number of valence electrons. So we know, we know that nitrogen has 5 valence electrons. Okay, hydrogen has 1. If we think about how these electron pairs are shared, I'm going to kind of color code these. Let's think about these bonds as being 1 electron from nitrogen, and let's go just yellow, 1 from hydrogen. Right? If we think about that, we've got hydrogen supplying 1 valence electron in each case. Hydrogen does have 1 valence electron, so that matches up 1 and 1. Nitrogen should have 5 valence electrons. Based on what we see here, it's only supplying 4. That shows that the nitrogen is where the electron was lost. So we can show that by putting a positive charge on that nitrogen. Okay, with that plus sign in the circle, that's called formal charge. We're not going to get super into this. Yes, there's a little bit more about formal charge below this in your notes, but really we're just checking to see, does the number of valence electrons that is represented in the Lewis structure from shared electrons and non-bonded unshared electrons match up with the number of valence electrons for that atom? If it doesn't, then we're going to show that formal charge. Okay. Let me give you another example. Oh, let me pick one. That's not going to be too crazy. Let's just do, let's do cyanide. That'll be fun. Cn minus. This is cyanide. This will give us some practice with multiple bonds as well. Okay, so carbon, 4 valence electrons. Nitrogen, 5 valence electrons. The negative sign means that we are going to gain an electron. So I'm going to add in 1 more. This is going to give me 10 valence electrons to work with. Okay, carbon, nitrogen. Okay, that's only 1 pair of electrons. I've got 8 more to use, 8 more electrons total. So I'm going to start placing them around the outside. So there's 2, 4, 6, 8. Okay. Now, what we want to do is we want to move electrons so that we have a full valence shell of electrons surrounding each of our atoms. That's not happening right now. Nitrogen has 8, right? 1 bond and 3 lone pairs of electrons, but carbon only has 4. So we're going to need a multiple bond. Okay, I'm going to take a pair from nitrogen and turn it into a double bond. That's a little bit better. Nitrogen still has 8, but carbon now has 6. So we're going to do that one more time. We're still going to want to take a lone pair from nitrogen and switch it to give a triple bond this time. Okay. Now we want to think about these electrons and where they are going to be associated, I guess, in terms of our bonding and non-bonding electrons. Right. So if I'm going to color code this, let's say I have 5 valence electrons in my structure that are surrounding nitrogen that are, let's call them belonging to nitrogen, right? Because while there's 8 electrons surrounding nitrogen, 3 of those electrons are being shared with carbon because they're coming from carbon. Okay, if I do the same thing, let's use green. There's 1, 2, 3, 4, 5 valence electrons for the carbon. Okay, now, do these match up? Yes or no? Okay, nitrogen has 5 valence electrons, and in the structure, there are 5 electrons around it. So that works out. Okay, but carbon should have 4, and it's got 5 here. So that's where our negative charge comes from. I'm going to redraw these real quick. Whoops, that's not the right color. And then I'll put in my formal charge. So there's N, there's my lone pairs. So I'm going to do 2 things. Okay, I'm going to show that there is an extra electron on carbon by putting that negative sign in a little circle. I also want to show that there has been a whole electron added in by putting my whole Lewis structure in brackets and putting that negative charge on the outside. Okay, that's how we look at our polyatomic ions. Okay, again, a couple different things we need to do. Put your whole structure in brackets with your charge on the outside, and then see where your extra or missing electron is and represent that with a plus or a minus sign, respectively. Okay, so you got some more opportunities to practice Lewis structures here on this next page, both part 1 and part 2. And then you're going to have lots of opportunities to practice on worksheet 2 in your problem set. So please make sure that you reach out to your teacher with any questions that you might have, and happy Lewis structuring.